Hello everyone, welcome to another video on statistics, and I'm still focusing on statistical inference 1, and I'm looking at the 2023 academic year assignments of STA 1502, and I am busy with assignment 1. In the previous video I looked at question 1, and today I'm starting with question number 2. As I promised, I'm going to go through the entire of this assignment and then move to assignment 2, 3 up to assignment 4. All right, so let's go to question number 2 then. Question number 2 says here, consider the following independent random samples drawn from two normal populations. Assume that the two population variances are equal. I've underlined that statement because it means something. As you see, when we start performing our calculations, we have two samples, sample 1, sample 2, and we have the three pieces of information provided. Sample size for sample 1 is 16, sample 2 is 13. Sample mean for sample 1 is actually 34.6, and then sample 2 32.2. And then we have sample standard deviation. The moment you have been given a sample standard deviation, you know the only way you can use a z-test is when the sample sizes are 30 and above. So in this case, the sample sizes are below 30. We're going to use the student t distribution. All right, the question says the e-tutor wants to determine whether there is a difference. You see here in question 1, you remember they used the word differ. Now here it changed to whether there is a difference between the two population means. And the requirement is that we construct a 99% confidence interval for the population mean difference. All right, so like I did in the previous video, I'm going to go through this from a hypothesis testing perspective, where we go through all the 6 steps and then come back and check for the correct answer. So let's go this page 1 actually, page 1, and we have STA 1502. We're dealing with 2023 academic year, and this is question number 2. We've done question number 1, remember, in the first video. So step number 1, we are supposed to write down the null hypothesis and the alternative hypothesis, H0 and H1. Now, if you would recall, here it says the e-tutor wants to determine whether there is a difference. It means we're going to say there's no difference in our null hypothesis. In other words, mu1 is equal to mu2. And this implies that the difference is actually 0. This is important, and let me put it in a rectangular box because we're going to come back here and take it and use it in our determination of the test statistic. And so, because the e-tutor wants to determine whether there is a difference, we're going to say there's no difference in our alternative hypothesis, so mu1 is not equal to mu2. That obviously not equal to means we have a two-tail test. Two-tail test. If you remember in the first video, I explained it, and I'm going to explain it again. So this implies that mu1 minus mu2 is not equal to 0. So that's step 1. Let's move to step number 2. In step number 2, if you remember, this is where we have to state the alpha level. And in this question here, we've been given a confidence level, 99% confidence interval of the population mean difference. So that's the confidence level, and we need to determine level of significance, alpha, and alpha is always 1 minus the confidence level, which is in this case 99%, which is 0.99. So performing our calculation here, we're going to get 0.01. Let's just check here. 1 minus 0.99, 0.01. Yes. Because we have a two-tail test, we have to divide this value by 2. So we're going to say, therefore, alpha over 2 is going to be 0.01 over 2, and the answer is 0.005. This is alpha over 2 value, right? And because we're using student t distribution or student t test, we're going to also be required to determine what we call the degrees of freedom. I write df, but the symbol for degrees of freedom is actually this one here. That is the symbol for degrees of freedom, but most students are not able to write that, so I write df just to simplify life for them. So it's in this case, because we are told, remember, we are told that the assumption is the two population variances are equal. We are going to use this simple formula, n1 plus n2 minus 2. So what is n1? Well, the sample size for sample 1 is 16. The sample size for sample 2 is 13. So this is n1 and that's n2. So we're going to say here 16 plus 13 minus 2, and that's 29 minus 2. The answer is 27. So that completes step number 2. You determine the alpha level and therefore alpha over 2 for two-tail test, and then you work out the degrees of freedom. Step number 3, if you remember, is the step where we determine what we call the critical value. And the critical value by definition is the value that separates the rejection region from the failed to reject region. So here we're going to use the t-test. So we'll say t-crit. T-crit, I use the crit there to separate it from the statistic. But some books will just write t, so just be careful here. This is going to be t. We write down the alpha level, in this case alpha over 2, which is 0.005, and then we write down the degrees of freedom, 27, and then we pick this information from the t table, t distribution table, and here it is. This is the t distribution table, and here we have for two tails, single alpha, and then for one tail, in other words, in each tail. Let me just take advantage of this and explain what I'm trying to say. When we talk about a two-tail test, we're basically saying, this is the story we're saying. You have a rejection region there and then another rejection region here. So it means you have two tails then, the upper tail and the lower tail. For a single tail one, obviously, you're going to have either this part here only or on the left-hand side there. This is right tail. For a right tail test, in our hypothesis, it should say that mu1 is greater than mu2. You're going to have this. If it says mu1 is less than mu2, obviously the shading will be on the left. It will be there. That will be your tail. So left tail test, right tail test. And in this case here, it's mu1 not equal to mu2, not the specific direction. Right, so now that is explained, let's come here. If you remember, in our calculations, we found that for a single tail, this is for a single tail. For two tails, it's alpha, which is 0.01. That's for two tails. For single tail is this. So if you come here, for a single tail, there it is, alpha over 2. This is the value we got, 0.005. And of course, for a single tail is, for two tails, the upper and the lower combined is 0.01. So our degrees of freedom, 27. So you move down to 27 and then move across. And then where these two lines meet is actually 2.771. That's our critical value. So that is the value we read from the t distribution table, 2.771. That is our test statistic. And because we have a two-tail test, it will be better for me to just indicate the plus or minus there. It will be better for me to indicate the plus or minus sign. I'll come back and fix that, so that of course that is the test statistic, but we put plus or minus because, like I explained, you are supposed to have a critical value there and another critical value there. So this one here, by symmetry, remember 0 is right in the center there. By symmetry, the value you have here, just put a minus in front, you get the value there. That's why you must have plus or minus. All right, so I'm going to come and fix that. Now that is step number 3. In step number 4 is where we now have to determine what we call the test statistic. Now, like I've said, we are going to provide all the necessary information on each question, because in this assignment, they require the students to determine the confidence interval. In an exam, they would actually want you to determine the test statistic and all that information. So that's why I said I'm going to provide all the information on each question. Right, let me put the plus or minus here before I forget. So this would be plus or minus, right? But don't lose focus of the fact that our test statistic is 2.771. The plus or minus is because of the fact that we have a two-tail test and because of symmetry. Right, let's go to step number 4. And in step 4, looking at the space I have here is not sufficient. Let me just move to the next page for step 4. I'm going to move to the next page for step 4 because there's a lot of calculation involved there. All right, step 4, and this is going to be my page 2. Step 4, we need to determine the test statistics. Now here, let's list down the information provided. Data. What is the data here? Sample 1. And then I have sample 2 here. In sample 1, N1, as you saw, is 16. N2 is 13. Now, in mean of sample 1, X bar is 34.6. Let me show you. Here it is, 34.6, and then here we have 32.2. X bar 2, 32.2. And then we have sample standard deviation of sample 1 is 4.8. There it is, and there 5.9. So 4.8, and here S2 5.9. Now this question here says to us, assume that the two population variances are equal. Because of equality of variances, basically the question is saying sigma 1 squared, that is variance of population 1, is equal to sigma 2 squared, that's variance of population 2. Those two numbers are equal. Because those values are equal, because of this condition here, I'm going to be required to work out what we call the pooled variance. So S subscript P for pooled, like this. In other words, the two samples are put together and then the variance is determined. Pooled sample variance, the formula says N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared divided by the degrees of freedom. Remember the degrees of freedom? Worked out already? I told you that because variances are equal, the degrees of freedom is just going to be N1 plus N2 minus 2. That is the denominator in this case. So we're going to have N1 plus N2 minus 2. Because of the equality of variances, we have to determine this. Now let's perform the substitution. N1 is 16 minus 1, and then S1 is 4.8. We're squaring that, plus N2 is 13 minus 1 times S2 is actually 5.9. We square that and we're dividing that by 16 plus 13 minus 2, which is basically 27. And the calculator here should say, so this is 15 times 4.5 squared. 15, let me go up, okay. 15 times 4.8 squared plus, this is 12 times 5.9 squared, and we're dividing that by 27, as you would recall that this is 29 minus 2 is 27. The calculator here says 28.27 and many ones. So let me just put together 4, rounding this off to 4 decimal places, which is not what I'm usually used to, but let's just carry that one this way for the sake of time. So this is the sample variance. We're needing it for the calculation of the test statistic, which I want to do straight away now. The test statistic, so T stat, remember, the formula says x bar 1 minus x bar 2 minus the hypothesized population difference all over the standard error of the difference between the two sample means. I'm going to say that again. The standard error of the difference between the two sample means. So how does the standard error look like? Standard error looks like this. Sample pooled variance squared, multiply this by 1 over n1 plus 1 over n2. Now, let's perform our substitution. The numerator, this value here is right here, 34.6. 34.6 minus 32.2, there it is. And then minus the hypothesized difference. If you remember the hypothesized difference, I told you I was going to put in a rectangle. There it is. We need it for the calculation of the test statistic. So we have 0 here. Standard error, obviously, it's going to be a substitution of this guy here, which is 28.2711. And then we say 1 over n1 is 16 plus 1 over n2 is 13. Like I told you in the previous video, I like to punch the whole information into the calculator one time. So in this case, we're going to say 34.6 minus the 2.2 all over square root of 28.2711 open brackets 1 over 16, and then we have plus 1 over 13, and then we actually close that bracket, pressing the equal button. My calculator says 1.2089. 1.2089. That is my test statistic. Right. Now, after this, I also want to work out, like I told you, the standard error. And then we're also going to look at the EBM, right? Error bound for the mean difference. Let's go to page number 3. In page 3, on page 3, we need to work out the standard error of the difference between the two sample means. Remember, for a case where variances are equal, population variances are equal, it will be the denominator here, that expression. So it will be that expression. So we're going to say SP squared 1 over n1 plus 1 over n2. And so what does this simplify to? It simplifies to, let's put in what we know, 28.2711 open brackets 1 over 16 plus 1 over 13. We saw this from the previous calculation here, that information. Hopefully you can see it there, that information there. Let me get the answer down. The beauty of this is that if any of our calculations here are incorrect, then the solution that comes out there will also be incorrect. So let's perform the calculation here. Square root of 28.2711 open brackets 1 over 16, and then we're going to say plus 1 over 13. Close that bracket, press the equal button. The answer is 1.9854 if I round out to 4 decimal places. 1.9854. Right, 4 decimal places. This is our standard error of the what? The difference between the two sample means. And then I also need to work out EBM, error bound for the mean difference in this case. So let's look at EBM. If you remember, EBM, error bound for the mean difference, because we're dealing with two populations here. is going to be, remember we're dealing with t now, t over 2 times the standard error of the mean difference between the two populations. So the critical value we obtained, if you remember, in step number 3, the critical value we obtained in step number 3 is 2.711. That's our critical value. I said plus or minus, of course, but when it comes to here, we take the positive value, 2.771, and then times this number here, which is this one here, 1.9854. And our solution is 2.771 times 1.9854. 1.9854. My calculator says 5.5015 to 4 decimal places. So that is EBM, error bound for the mean difference. From here, I'm going straight to confidence interval. Now here we're dealing with 99% confidence interval. So my next calculation, which is what this question is about, 99% confidence interval, CI, for the population mean difference. In other words, the difference between the two population means will be equal to the difference between sample means plus or minus error bound for the mean difference. So let's put in the information we have there. Data provided, here it is. These are the numbers we're dealing with. X bar 1, 34.6, and then we have X bar 2, 32.2. So this is 34.6 minus 32.2, and then we are supposed to say plus or minus EBM is this number here, 5.5015. This is going to be equal to, let me subtract the 34.6 minus 32.2. My calculator says 2.4 plus or minus 5.5015. So my final solution is going to be, maybe final but one step, we are going to say 2.4 minus this value to get the lower bound, 2.4 minus 5.5015. Yeah, 2.4 minus 5.5015. Right, my answer to 3 decimal places is going to be minus 3.102, and then the upper bound is going to be, I'm changing that minus sign to plus sign, so the answer is 7.902. So 7.902. Basically, we are saying that mu1 minus mu2, we are 99% sure or confident that this difference here is between this number here, 7.902, and minus 3.102. So this is what we're saying. We're 99% confident that the mean difference is in that interval. Right, let's move on now to step number 5, which is, we've done all the necessary calculations here, but I'm just completing the 6 steps or 5 steps. We will leave out the last step, which is a conclusion step. Let's go to step number 5, the decision rule step. Now this is page 4. Decision rule says reject the null hypothesis if the test statistic, remember we're using a t here now, is greater than the critical value. Now, or obviously less than the negative value of this. If you saw it in the previous video, we're saying this is the same. Remember, this number here is actually 2.771. So we are saying, or if the test statistic is actually less than the negative of this one, which is that. Two conditions, this one or that one that we're testing here. Let's show you the distribution curve, then the normal distribution curve. looks like so. There you have it. Obviously we have 0 in the center, and 2.71, let's say, is somewhere here, 2.771, and therefore by symmetry here you must have minus 2.771. And if you remember this part here, we said this is alpha over 2, and its value is actually 0.005. If you remember that, we said it in the previous video, and I'm saying it again. This part should also be shaded because we have the two-tail test, the upper tail and the lower tail. The lower tail, its shaded area is also alpha over 2, which is exactly the same as that one on the right hand side there. The central part is 99, the unshaded part is 99%, or 0.99 as the area in the unshaded part. Now let us compare our test statistic and our critical values. If you remember the test statistic calculated, this is our test statistic. There it is, 1.2089. The question is, where do we place this value? Do we place it there? It's a positive value, obviously. It's the right hand side of 0. Do we place it after this or before this? Obviously, you can see that that answer there is before this number here. Let's just say just under half, so somewhere around here. This is where we're going to have 1.2089. So it is in the fail to reject region. So we're going to say, therefore, we fail to reject HO. If we fail to reject HO, it means we support it. Like I told you in the previous video, this statement here means that the mean difference of the hypothesized mean difference must be in our confidence interval, because we failed to reject the narrow hypothesis. So we failed to reject the narrow hypothesis. In other words, we support this. It means that answer there must be in the confidence interval, because the two say the same thing. And if you look at these numbers here, it is correct that 0 is a number between in that interval, because this is 7.902, this is minus 3.102, so 0 is inside there. That is why we failed to reject HO. This confidence interval and our traditional approach should say the same thing. Now the p-value, convince yourself using Excel, you can actually check this from a t distribution curve, or from the t-table. You do not get the exact value of the test of the p-value. However, what you should find is that the p-value is actually greater than the critical value. Is actually greater than alpha level. Let me repeat that. What I'm saying here is that the p-value is actually greater than alpha value. And what is our alpha value according to this? 10%. So it's actually greater than 10%. Obviously, we are saying this is 0.10. So the p-value, if you're using Excel, please confirm this. The p-value is bigger than that. And because p-value is bigger than alpha, we cannot reject the null hypothesis. We reject the null hypothesis only when the p-value is less than alpha level. All right. Now let's go back to our question and check which one is the required solution. Here it says the confidence, 99% confidence interval. Like I told you, the correct answer is this one, which is exactly what we got here. If you can see, and there is our solution there. Exactly minus 3.102, comma 7.902, which is the answer that I have indicated on the question paper. All right, in my next video, I'm going to be looking at question number 3. Number 3 is slightly different from what we've looked at so far in the two questions. This one here is what we call a matched pair experiment. You'll see how we approach it, and I'm going to provide the detailed explanation on that one as well, and how to go about answering that in an exam or assignment. All right, if you're new to this channel, please support us by subscribing and inviting friends to subscribe, and sharing these videos and liking them. I cover these videos in a fashion that takes on board everybody. I am slow in the way I explain these concepts. That does not take away by any means the authority I have in these concepts and these disciplines that I cover in my on my channel here. All right, I'm trusting that you found this video useful, and if you did, please, like I said, support us, and we will be very grateful. All right, see you next time.